Hi Year 12, welcome to the next part of particle physics. We're going to be looking in general, in this section we're going to be looking at quantum mechanics, and in this video we're going to start by looking at the first kind of quantum model of the atom, which was proposed by Niels Bohr. Specifically, really what we need to know about in terms of the exam is what happens according to this model when atoms interact with other particles, become excited, and subsequently become de-excited and emit light. So we're looking at the process of excitation and de-excitation of atoms. So we're going to start by looking at the classical atom. So the model of the atom that we had before quantum mechanics, before Niels Bohr came up with his idea of how atoms worked. And the classical atom would be a nucleus in the center with electrons around the outside. So if we think about a hydrogen atom, we've got one electron orbiting one proton. So it's behaving a little bit like perhaps a planet orbiting a sun in the solar system. However, the difference between what we've got here and a planet orbiting a sun is that the electron is a charged particle. And so if a charged particle is moving in a circle, that charged particle is accelerating, and accelerating charged particles must emit radiation. So in this model, the electron would have to be constantly emitting radiation and therefore losing energy. If it was losing energy, what should happen is the electron should spiral inwards towards the center of the atom. So a major problem with this idea of the atom is that it's not stable. There were further problems as well. It was observed that atoms in a gas which were excited would give out light. So, for example, atoms of hydrogen and helium and other elements in the sun give out light. There are other ways of obviously exciting atoms. You basically just need to heat up a gas. But if you look at the light that's emitted from these excited atoms, these heated up atoms, or you could also excite them by passing an electric current through the gas. If we pass that light into a spectrometer, which we could think of as sort of simplistically being a slit that the light passes through, and then a prism, and the prism splits that light up, refracting it out at different angles. If you pass that light through a spectrometer, what you see for a specific gas is not a continual range of different colours, but you see what are known as spectral lines. So if we think about this as being increasing wavelength along here, we would see different colours being emitted from the gas, but they would only be at very distinct wavelengths. So we might have a blue spectral line, you might have a yellow spectral line, maybe a slightly different wavelength of yellow there, and then as we go up to longer wavelengths we might have a red spectral line. And of course you could also have spectral lines in the non-visible parts of the spectrum, so infrared or more likely to be ultraviolet and shorter wavelengths. So these spectral lines have distinct frequencies, and there's no way that the classical model of the atom could explain that. So there are two sort of really key kind of failures of the classical model of the atom. So if we move on now and look at what Bohr said, the Bohr atom is really sort of one of the first key parts of quantum mechanics. It's no longer really the best description that we have of the atom. It's a very kind of simplistic model really compared to what we understand about the atom today, but of course a amazingly sort of crucial step at the time. So what Bohr said was that in the atom, the angular momentum of the electrons is quantized. It means it can only have certain values. Now, we don't study angular momentum in our mechanics, but essentially what that means, another way of thinking about it, is that the energy of the electrons is quantized. So we arrive at this idea, which is now very familiar to us from GCSE chemistry, that an atom has a nucleus in the middle and it has these electron shells. So we can have maybe 2 electrons in the first shell and up to 8 in the second shell, and so on. So electrons can, in the inner shell, have a lower state of energy, the lowest possible state of energy, and in the next shell they have a higher energy. But electrons are not allowed to have energies that fall between those two energy states. So only certain energies are allowed. So we talk about the energy being quantized. Now that's actually quite an amazing idea if you think about it. If we applied that same principle to everyday objects, we'd find that very strange. If we applied it to the idea of the kinetic energy of a car, it's a bit like saying that you have a car that's allowed to drive at 10 miles an hour or it's allowed to drive at 20 miles an hour, and it can change between those two states, but it can't go at any speed in between 10 or 20 miles an hour. We have this leap from the lower energy state to the higher energy state. So if we look at what the values of these energy states are, so Bohr looked at the hydrogen atom initially as a sort of simplest atom that we could look at, but we could draw these diagrams for other atoms as well, but we're going to look at hydrogen because it's simple, because we only need to think about one electron. So the lowest energy state, we label the energy states with numbers, which we denote as n. So we've got the n equals 1 energy state is the lowest energy state, which we also call the ground state. And following from this kind of idea, Bohr was able to actually work out what the values of these allowed energies were. The lowest energy state, the ground state energy, the electron has an energy of minus 13.6 electron volts. The next highest energy state, so n equals 2, the energy there is minus 3.4 electron volts. And we can keep going. So the n equals 3 be minus 1.51 electron volts. N equals 4. And you'll notice that these energy levels are getting closer together as you go up. The energies are negative because essentially what we need to do, I'm not going to go into the sort of reasoning for why this is at the moment, but what we need to do is the very highest energy level, which is the energy level of a free electron, so an electron that has escaped from the atom, we need to define as 0. So this is what we would label as the n equals infinity energy level. So in between what we've drawn here up to 4, we've actually got an infinite number of energy levels all getting increasingly close together. And when we get to n equals infinity, we say that the electron at that energy has become free, and we give that free electron energy level a value of 0. So once we've defined that as 0, because we need to do work to remove the electron from inside the atom, so if we're going up through these energy levels, we're doing work, we're increasing the energy level, the values of the electron within the atom therefore have to be negative. Okay, so we've got ground state up through an infinite number of energy levels up to the free electron energy level at the top. Okay, so if we think about an electron that's going to start in the ground state, it can be excited. So we would represent that on this diagram by drawing an arrow going from where it starts to where it ends up. It could be excited into any energy state. We could also give the electron enough energy so that it gets all the way to 0, in which case it would escape from the atom, and we would call that ionisation. Okay, so we've got excitation and ionisation. So how can these two processes happen? There are two main ways that we're going to consider. Firstly, the atom could be involved in a collision with another particle. So perhaps most usually this might be an electron. In this case, some of the energy of that colliding particle, some of its kinetic energy, is going to be transferred to the electron within the atom, and that's either going to cause excitation, or if enough energy is transferred, it could cause ionisation. So in order for either of these two processes to happen by particle collision, the only thing we require is that the colliding particle energy must be greater than or equal to the change in energy that we require. So I've used delta E here. So for example, if we were talking about the excitation here from 1 to 4, then delta E would be the difference between minus 13.6 and minus 0.85 electron volts. Okay, so key thing here in a particle collision, so electron comes in, collides with the atom, collides with the electron within the atom. We don't need that colliding particle to have an exact amount of energy, we just need it to have a sufficient amount of energy. Okay, the other way that excitation or ionization can happen is by the atom absorbing a photon. So a photon comes along and it's absorbed by the electron within the atom, and that can cause excitation, or again it could cause ionization. Now the key difference here is a photon can't lose some of its energy. A photon either gives up all of its energy, it's absorbed and stops existing, or it doesn't. So for the case of photon absorption, we require the photon energy to be exactly equal to the change in energy of the electron. Okay. Right, finally, we're going to just think about what happens when the atom becomes de-excited. So if an electron moves up into a vacant energy state within the atom, it will, within a very short amount of time, talking I think probably picoseconds, that electron is going to fall back down into a lower energy state. It's going to keep falling down until it reaches the lowest energy state that it's possible for it to be in. So if we look at this example that we were talking about, so perhaps this hydrogen atom, there's one electron in the ground state, it's excited up to the n equals 4 energy level, it's going to come back down, and it can do that in various ways. So it could take one giant leap back down from 4 to 1. Okay. It could, however, do it in a different way. It could jump from 4 down to 2, and then from 2 down to 1. In that second case, it's going to emit 2 photons. So when these electrons, when the atom de-excites, when the electron drops back down, the energy is transferred back out of the atom as a photon. For each step it takes, it releases 1 photon. So if it does that in one jump, then it's going to release 1 photon, and the energy of that photon is going to be that same delta E, the difference between minus 13.6 and minus 0.85. If it goes from 4 to 2 and then 2 to 1, it's going to release 2 photons. The first photon is going to have an energy which is the difference between 0.85 and 3.4, and the second is going to have a higher energy, the difference between 3.4 and 13.6. There's another final way that it could de-excite, and that's by doing a smaller step first and then a double step from 3 down to 1. So if we think about these de-excitations we've drawn on here, we've got 1, 2, 3, 4, 5 distinct photon energies, and it's these distinct photon energies that result in these distinct frequencies of these spectral lines, because of course we've got our relationship for a photon that the energy of the photon is proportional to the frequency of the light. Okay, that's it for this one.